Alright, question number 1 on the heat equation. What we're asked to do here is we are asked to we are asked to convert calories to joules. Now notice this is capital C calories, which are dietary calories, and we're converting them to joules. So let's go ahead and get started with this. What I have to start with is 240 dietary calories. So I'll say I have 240, and that's capital C calories. I don't want capital C calories, so I'm going to put them in the basement. Capital C calories. One of those equals 1,000 little c calories. I know, it annoys me too. Okay, now I'm out of dietary calories into regular calories, but I don't want calories, I want joules, so I'm going to put the little c calories down below. And what I see here is that one of those equals, according to this, 2.4 joules. So I'm going to put, 4.2 joules. And that tells me that what I've got here is 1,008,000 joules. Now I know that's 4 significant figures, and I really should be limiting myself to 2, but I'm just going to go with it. Okay, now the second question then is how high? Now remember, high is distance, which means I'm going to be using the work equation. So that means the equation I have to use is work equals force times distance. Those are terrible F's and D's. Okay, and so now in order what I'm trying to solve for is how high, which is distance. So I need to know a force value and a work value. Now remember, force is measured in newtons, and here I have newtons, so I'm going to substitute that in. I'm going to put my 780 newtons where F was. I'm solving for how high, which is a distance, and that means I need to know how much work is done. Now work is measured in joules, and here I have how many joules are in a can of soda. This is for real, folks. 1,008,000 joules in a soda. That is scary. But here you go. I have 1,008,000 joules, and when I solve that for D by dividing both sides by 780 newtons, what that leaves me with in this case is the distance equals 1,292 meters. That's pretty amazing. Alright, let's just move this on up here. Now what I have is, let's make it a little bit larger. Alright, here's Chad Rowan. What do I know about this? How many joules of energy would he transfer to the water? Now I'm looking for joules here. Let's see what information I have. I know how much my sumo wrestler friend weighs. I know meters is how high he was. Hey, you know what? I have newtons and I have meters. Once again, that's going to be work equals force times distance. And what I've been asked to find in this case is how many joules of energy is he going to transfer to the water. Well, the joules he's going to get is basically when he climbed up that ladder. Here, I'm just going to draw this for you. So here I have a ladder. I have my sumo wrestler was down here, and as he climbed up the ladder to here, he had to do a certain amount of work, and that work is going to be equal to his weight, that's how much he weighed, times the distance that he went up, which was 3 meters. He climbed up 3 meters. So what we get there is 2,330 newtons times 3 meters is going to tell me that the work he did going up there was 6,990 joules. So now the next question says, how many calories of energy would he transfer to the water? So really all that means then is I've got to convert this many joules into calories, because when he hits the water he's going to stop moving and all of his energy is going to end up as heat. So I want to know how much heat. Well, it's going to be this much heat energy, but I want to express it in calories. So in this case I just have to start off with 6,990 joules. I don't want joules. I put them in the basement. I like to turn them into little c calories. I'll put those up above. And the conversion factor is that 1 calorie equals 4.2 joules. And so when I do that, I find that he is going to transfer 1,664 calories of energy to that pool. And now our next question, let me just lift this up a little bit here. Alright, and now we get to the next question where it really matters here. Now we're going to use our heat equation here. It says, how much would it change the temperature of the water? Now let's look at this heat equation. Delta Q means the change in energy of a system, how much heat energy it absorbed or released. All right, how much heat energy it gained or lost in calories. M is the mass of the object in grams. Delta T is the change in temperature in degrees Celsius. And Cp is specific heat capacity. How hard was it to make it get hotter or colder? So let's just try this here. I'm going to use this equation here, and I'm going to substitute everything except for the change in temperature, which is delta T. So the first thing you need to know is delta Q. Delta Q is measured in calories, and I happen to have how many calories right here. So I'm going to say 1,664 calories equals the mass of the pool. Now the mass of the water in the pool is right here, 36 million grams of water. By the way, this is a realistic mass. All of these values are realistic. So I have 36 million grams, yes, I measured, times the change in temperature, the delta T, times the specific heat capacity of water. So Cp, specific heat capacity, well, the specific heat capacity of water is 1, which means it takes 1 calorie to make 1 degree of water 1 degree hotter. So now all I have to do is solve this equation here for delta T. I have to divide both sides by 1, done. Then I have to divide both sides by 36 million. So I'm going to divide both sides by 36 million. Oh, that's a lot of zeros. Alright, I think that's the right amount. And when I do that, what I'm going to find is this. The change in temperature is 4.6 times 10 to the negative 5th degrees Celsius. That's not a big change in temperature, but it's measurable, and that's what happens. Well, I got to tell you, I love this heat equation. I think it's a lot of fun, so let's do the next one here then. Alright, I've got a pot of water. I'm going to bring my heat equation up here. I love this mobile heat equation of mine. Alright, let's see what I'm trying to find. My thing is I first look for the word that makes it a question. It says, how much does the temperature of the water change? So I'm looking for delta T. And so let's see here. That means I need to substitute in everything else. So, first thing I got to know is what is the delta Q? And the delta Q is right here. It's how many calories, so it delta Q'd by 86,152 calories equals the mass of the water. In this case, the mass of the water is 3,560 grams times the change in temperature times the specific heat capacity of the water, which, why did I write that? Because actually that was silly of me. The specific heat capacity of water is 1, so I'm just going to go ahead and erase that. Sorry about that. And that's 1. Whoops. And that I did it again, and that's 1. Alright. Now when I solve for delta T, what I'm going to find then is that delta T in this case equals 24.2 degrees Celsius. 24.2 degrees Celsius is how much the temperature of water would change, and so it's going to get that much hotter because I'm heating it up. So now to answer question B, it says what is the ending temperature of the water? So what I do is this is how much the water changed temperature. It changed 24.2 degrees. So what did it start off at? It started off at 17. So all I have to do here is say, well, the water was 17 degrees Celsius, and then I made it go up by 24.2 degrees Celsius. So the ending temperature of the water is going to be 41.2 degrees Celsius. So the thing to remember here is this equation solves for the change in temperature, but if I wanted the ending temperature, I have to take the change in the temperature and add it to the starting temperature or subtract it depending on whether I'm heating up or cooling it down. This is fun. Let's keep going. What do we got here? Alright, it says now, whoops, I didn't mean to do that. Okay, let me lift this up even higher. Okay, if the pot contained ethanol instead of water, how much would the temperature have changed. So now I have to look at the CP values above. So I have to find what is the CP of ethanol, and it ain't going to be 1. So let's just see what we got here. Go back to the beginning. The specific heat capacity of ethanol, it shows me here, is 0.60. So let's go back down to that question. So I got 0.60. Look at all my little hour. Okay, so here's what I got. All right, I've got to say, all right, whoops, I missed. Oops, I did again. All right, I keep doing that. Eric, stop doing that. Dang it. Well, okay, there you go. Okay. All right, I'm going to get this. Here we go. Okay, so now if I want to know how much the temperature would have changed if I added 86,152 calories, that's my delta Q, equals the mass. Now in this case the mass is 3560. I still want to find what is the delta T, but in this case, instead of the specific heat capacity being 1, which it is by definition for water, I find instead for ethanol, it's 0.60. And what this tells me is it takes 0.60 calories to make 1 gram of ethanol 1 degree hotter, instead of 1 that it takes for water. So now I just had to get delta T by itself. So that means I have to divide both sides by 3560, which makes this go away. Boom. Now I have to divide it by 0.60. So I'm just going to say divide it by 0.60. And you know what? I'm just going to enter my calculator this way. I'm going to say this divided by this divided by this. And when I do that, what I get is the change in temperature. In this case, should be more because it's easier to heat up the ethanol. And what I'm going to find now is it changed 40.3 degrees Celsius. Considerably easier than it was for the water, which only changed 24.2. Because what the specific heat capacity is telling me is how hard is it to heat it up. Okay, let's look what we got next. Alright, next one. Oh gosh, look what happened here. I ran out of room for number 3, so I'm going to do 3 on a separate sheet. Okay, so we're going to do this one here on a blank slide. Give me a second here. Okay, so for this one, what I have is 3 pieces of metal. They all have the same mass, but one of them is made out of copper. One of them is made out of iron. And one of them is made out of aluminum. They've all been put in, they all have the same mass, and they put in the fire for the same amount of time. And what I've been asked to find out is which one will be the hottest after being heated for 20 seconds, an equal amount of time. Well, to do this, we have to look at their specific heat values, which are listed at the top of your paper. So we find is this: the specific heat capacity of copper is that was not right. Is 0.092. Iron is 0.11, and aluminum is 0.21. Now here's the way to interpret this. What this really means is this: that if you want to make 1 gram of aluminum 1 degree hotter, you have to add 0.1 calories. If you want to make 1 gram of iron 1 degree hotter, you have to add half as many calories, 0.11. And if you want to make 1 gram of copper 1 degree hotter, all you have to add is 0.092 calories. So basically, these numbers for specific heat capacity, which is represented this way, specific heat capacity, it's really a measure of how hard is it to heat something up. So when I say aluminum has a specific heat capacity of 0.21 and iron has a specific heat capacity of 0.11, basically what I'm saying is aluminum is 2 times harder to heat up or cool down. It's 2 times harder for it to delta its T. So now what we find then is I put them all in the oven for the same amount of time. Copper is the easiest one to change its temperature, so copper will be the hottest. and aluminum is the hardest to change the temperature, so aluminum will be the coolest. And the question I was asked was, which one ends up being the hottest? And the answer is copper. And the reason is it has the lowest specific heat capacity, which means it's the easiest one to change the temperature of. Alright, let's see what we've got here. Alright, we have a 324 piece of metal is taken out of an oven at a temperature of 232 degrees Celsius, placed in a container of water. Now when I put in the water, it loses this many calories of energy, goes into the water, so the metal cools down to this temperature. Now the first question I was asked is, what is the delta T of the metal? Sorry, it doesn't look like a delta here. Okay, what is the delta T of the metal? Well, you know what? In this case, I don't even have to use this equation, even though I wanted the delta T. Delta just means change in temperature. How much did the temperature change? Well, when it came out of the oven, it was 232 degrees Celsius, and it cooled down to 35 degrees Celsius. So all I need to do is find the difference between those two values, and it turns out, let's see, I've done the other page here, so it turns out that's like 197 degrees Celsius. That's its delta T. Alright, now, what is the specific heat capacity of the metal? Now I have to use this wonderful heat equation to find the CP. Well, I have to know the delta Q is measured in calories, and here's calories right here, so I'm going to take this and put it here. So I'm going to say 1914. I'm going to skip my units, naughty me. Okay, the next thing I have to know to use this equation is I have to know the mass of the material. There it is right there. It's 324 grams. 324 grams. Next thing I have to do is I have to know what is the specific, what is the change in temperature. Here's my delta T right here. The temperature changed that much. So I'm going to say, alright, times 197 times the specific heat capacity. Now I just have to undo what's done to specific heat capacity. It is being multiplied by 324, so I'll divide both sides by 324, and that will make this go away. Now it's also being multiplied by 197, so I'll divide both sides by 197. So what I'm going to do is I'm going to take my calculator, I'm going to enter 1914, then I'm going to divide that by 324, and I'm going to divide by 197, and when I do, I'll find that the specific heat capacity in this case turns out to be a whopping 0.03, and that's calories per gram degrees Celsius. Now, here's the thing, that might look like a really small number to you, but it's actually right. The thing to keep in mind is this: water has the highest specific heat capacity of any substance in the universe, and its specific heat capacity is 1. So you know if you've done it correct, your specific heat capacity is going to be less than 1. If it ever comes up more than 1, you did something wrong. Now it says here, use the specific heat capacity to identify the metal. So just like I can use density or melting point to identify a substance, I can also use specific heat capacity. So if you flip your paper over and look on the front side, that means that specific heat capacity here, 0.03, that is the same as lead. This is probably lead. Okay, now we're going to get to the stuff that really is at the heart of all this. This is what your lab is going to look like. You'll get something like this just on your test. I'm telling you, this is on your test. Wait a second, you know what? I need a specific heat equation. Give me a second here. Okay, pay close attention to this part here, because number 6 is really what it's all about. This is how we do what's called calorimetry. So let's just take a look at what we've got here. Alright, here's our scenario. We have a piece of metal with this mass here, and we have a container of water. Let's see. And what we're going to do is we're going to heat the piece of metal up to this temperature, and then we're going to drop it into this much water, which is at this temperature. And then, so the trick is, we've got to fill out one of these, a data table, a calorimetry table. And here's how these work. The first column refers to the water, because when we do calorimetry, we always use water, because water has a known specific heat capacity. And we usually heat up or cool down a piece of metal and then put it into the water. So you have to first figure out what the mass, starting temperature, ending temperature of the water is, and then do the same thing for the metal. Alright, so let's go ahead and give this a try now. Alright, let's just start filling in this information. First thing I know here is I have 250 grams of metal. So for the mass of the metal, I'm going to put 250 grams. And I'm going to keep reading here. Is held over flame till it, meaning the metal, reaches a temperature of 624. That's the starting temperature of the metal, 624 degrees Celsius. Okay, then the metal is dropped into 650 grams of water. So now I had to go to the water column and enter its mass, which is 650 grams. Now the next thing I got to do then is it says the water starts off at 22 degrees. That's the starting temperature of the water. So it's going to go in this box here. So I'm going to start off at 22 degrees Celsius. Sorry, honey, this is kind of weird. Okay, I was talking to my wife. Sorry about that. All right, and the next thing then I have to know is, let's see, after a few seconds, the temperature of the water, they're both at 67 degrees Celsius. Now, this is an interesting thing about calorimetry, is that they always both end up at the same temperature. So they both end up at 67 degrees Celsius. All right, so now the trick is, I've got to figure out what is the delta T of the water and what is the delta T of the metal. Now, because water has a very high specific heat capacity, it probably won't change very much. So let's see what we find. The water changed its temperature. I'm just going to say 67 minus 22, and what that gives me is it changed 45 degrees, and what we find is the metal had its temperature go down by 557 degrees Celsius. Armed with this information, once I have this data table all filled in, then I'm ready to rock and roll on the other questions. So let's just see what we got here. Okay, now it says use the heat equation to find out how much energy the water absorbed from the metal. So let's just go ahead and move this equation down here so we can look at it. All right, and in this case I am looking for how much energy, that's what delta Q is. So I'm going to say that the delta Q equals, now be careful what it says here. It says use the heat equation to find out how much energy the water absorbed from the metal. So I'm looking at the water now, okay? Turns out it'll be the same for either, but let's just go ahead and do the water first, okay? So the mass of the water, 650 grams of water. The delta T of the water is 45 degrees Celsius, so times 45 degrees Celsius, and the specific heat capacity of water, hopefully by now you're starting to remember, is 1. So therefore, the delta Q is going to be found by multiplying 650 times 45, and when I do that I find that the amount of energy that was gained by the water is 29,250 calories. Now, interestingly, that's also how much energy the metal lost, because the first law of thermodynamics says however much energy the water gained, it gained from the metal, so that's how much the metal lost. And that's the key trick to calorimetry, is to keep in mind that however much energy one part of the system loses is how much the other part gained, and vice versa. Now let's just keep going here. Now we're going to say use the heat equation to find the specific heat capacity of the metal. So now I'm going to do the same thing, but in this case I'm looking for the specific heat capacity of the metal. So I had to use all this information except for the CP. So remember, the delta Q is always the same for both of them, because however much energy the water gained, that's what the metal lost. So I can take the delta Q for the water and use it down here when it comes to trying to find for the metal. So I'm going to say 29250 calories of energy was lost by the metal. Now I had to be careful. In this case, the mass, we're talking about the metal now, so I had to talk about what is the mass of the metal. And the mass of the metal is 250 grams. It's very important to keep in mind who we're talking about. Now I had to use the delta T, and that has to be the delta T of the metal, because we're talking about the metal. Here's the metal, Here's its delta T. It delta its T 557 degrees Celsius times its specific heat capacity. So now what I have to do is I have to divide both sides by, I'm going to divide by 250. That'll make that go away. I'm going to divide both sides by 557. That'll make that go away. And what I'll find then is the CP of this metal turns out to be, I got to take a quick look at it here. I get, when I do my calculations, what I get is 0.21, and that's calories per gram degree Celsius. But I don't really care if you write down this, the units. But I do want you to know that what that means is it takes 0.21 calories of energy to make 1 gram of this stuff 1 degree hotter or colder. So now if I look at E, it says use the values to identify the metal. When I look up this in my list, I'll find that is aluminum. Hey, we're almost done now. Let's just keep going here. Alright. Let's just go all the way up here. It says, I'm going to look for the word that makes this a question. It says, what is the mass of the glass? So I'm looking for mass. That means I need to know all the other things. Let's see what I've got here. Okay. So I know the specific heat capacity is 0.19. So I'll say, alright, I'll say 0.19. That's great. Alright. And let's see, I need the delta Q, and the delta Q is measured in calories. And it says when I put it into, when cold water is poured, the glass temperature drops from here to here, and the water absorbs as many calories. Now remember, however many calories the water absorbed, that's what the glass lost. So I can use this calories and put it here. So I'll say 1136 calories. Now I will, let's see, I want to know what the mass of the glass is, so therefore I need to know what is its delta T. So let's see, it was 20, it dropped to 7, so 20 minus 7 gives me a delta T of 13. So I'm going to put in 13 here, and I had to solve it for mass. So to solve for mass, I have to divide both sides by 13. That goes away. Then I have to divide both sides by 0.19. So divide by 0.19. And what I find then is the mass equals, in this case, it's 460 grams. Alright, and the last question, then we're done. It says, why does dry sand end up hotter than wet sand even though both absorb the same amount of energy? And the answer has to do with specific heat capacity of water. The answer is because the specific heat capacity of water is very high, which makes it hard, making it harder to heat up than dry sand. Sorry for the terrible handwriting. Hey guys, good job.